Sure. Yes, I am. Okay. Okay, slide in. Okay. So we might be live. I think we have this 17 seconds change. Okay, welcome everyone. Thank you for joining us for today's webinar. My name is Alejandro and I'm going to be today your host. Today we are presenting Investigating the Variability of Accretion Binary Black Holes by Scott Noble. Scott is an assistant professor at the University of Tulsa and a senior NASA postdoctoral fellow since 2017. He got his bachelor in physics from Caltech, and then he did his PhD at the University of Texas at Austin. Then he moved to the University of Illinois at Urbana-Champaign, where he did his first postdoc. And then he moved to Johns Hopkins and RIT, Rochester Institute of Technology, as a research scientist. It is very nice to have Scott. He is an world expert in computational methods of general relativistic magnetohydrodynamics. That's a very complicated word, also known as GR-MHD, which he uses to simulate accreting systems about single and binary black holes. He's also very interested in exploiting modern high-performance computing facilities and techniques to solve astrophysics problems in the strong field limit of gravity. So remember that you can ask questions over email through our YouTube channel or Twitter, and then we will forward those questions to Scott at the end of his webinar. So without further ado, I'll turn it to Scott. Thank you.
Thank you very much, Alejandro, and thanks for the opportunity to speak today. I'll be talking about accreting supermassive binary black holes, and in particular, looking at the variability of the emission from these objects. So these are black holes that formed and developed in the centers of galaxies, and the galaxies merged, and all the gas around them accretes onto the black holes, and that accretion process then lights them up. And here, what you're seeing here is the X-ray emission from such a process, where the black holes are pretty close to each other. They're emitting gravitational waves, and they're emitting high-energy luminous X-rays. So we're hoping to be able to see both gravitational waves and X-rays vary as they inspiral and merge, as the black holes inspiral and merge. So this is, as Alejandro said, it is a rather complicated process. You have to do these supercomputer simulations, and we are using pretty novel techniques to solve these new problems. And so there's a large team of people that is assisting me, and also innovating new techniques for the team. And I list them here. And mainly we're based in Johns Hopkins, RIT, and NASA, and we're collaborating as part of this network. And if you want to see more papers or such from me, you can follow this web link here, and follow me on Twitter. Though I have to say I'm not too active on Twitter, but I hope to change that in the future. Coincidentally enough, it's Black Hole Week here at NASA. It's a social media campaign to just communicate our excitement for black holes. And NASA has created this really adorable cartoon shown in the upper right-hand corner here about an extraterrestrial tourist that wants to go visit a black hole. And so the narrator kind of teaches the alien how to be careful around a black hole and maybe advises against it. But anyway, so it's kind of a fun little set of media elements that kind of communicate some of the aspects of black holes. So if you teach younger students, or even a fun undergraduate course in astrophysics, it could be kind of a entertaining way of introducing black holes. And here I've listed some links and such to them, to the materials. And also, if you have a story about black holes that you want to share, please tweet it and hashtag Black Hole Week, and that way we can see what you're doing with respect to black holes. So yeah, I'm really interested in the strong field regime of general relativity. So general relativity is Einstein's theory of general relativity, and it tells you how space-time curves, mass curves space-time, and space-time controls how matter moves, gravitationally speaking. And it's not a force, it's really a curvature of space-time. Mass flows down or is affected by this curvature, and that's what we see as things being affected by gravity. And so this curvature can be actually time dependent, right? So bodies can move. So on the lower left-hand corner is a simulation of two black holes. It's an early simulation of two black holes in spiraling and getting closer and closer together. And they make gravitational waves. And these gravitational waves are ripples of space-time. So these are curvature waves in the space-time system. And they can emit energy and angular momentum away and allow the black holes to finally merge. And the merger process results in a burst of radiation that is very luminous, and we can now see. We've seen this happen thanks to LIGO. And so gravitational wave is a transverse wave, and it's a little different than an electromagnetic wave because it's a tensor wave. And so if the wave is going into the screen, those dots in the upper right-hand corner show you how those dots would deform as that wave passes by them. So there can be two polarizations, the left and the right polarization here, and that's how gravitational waves affect things. They elongate in one dimension as they squish in the other, and then vice versa during the next phase of the wave. And so we can use this to explore systems that are otherwise hard to see with light. They're often dark or small and not very hot, except for maybe the supermassive binary black hole case. In any case, it allows us to test general relativity in the strong field regime. It allows us to explore the theory of gravity in a way that no other means can, right? So this is the most extreme limit of GR that we have available to us in nature, and we can make use of it by measuring these gravitational waves. And we've done that. So I think this is coming through my headphones. I don't know if it's being transmitted, but this is the sound of gravitational waves, and it was first heard by LIGO or by anyone in September 14th, 2015. And in the upper left-hand corner here, you see the actual gravitational wave signal detected by LIGO Hanford and Livingston. These are two gravitational wave observatories, laser interferometers. That's what LIGO stands for. And they detected the signal. In the lower right-hand corner is just a simulation of what it would look like to see a field of stars behind the black holes merging. So the black holes are so compact, their gravity is so strong that they curve space-time, and they distort, they gravitational lens in a strong way the light that is emitted behind them. And so the field of stars is distorted in a really weird way. And you can see the two black holes in spiral and then eventually merge. You can see neat things like eyebrows, so like secondary echoes essentially of the lens system of light behind it. Note that this is a simulation, but it does highlight the fact that there's probably not a lot of gas around these black holes. Okay, so I'll come back to that. But of course, this was an incredible discovery. People had foreshadowed that there would be gravitational waves, but it was really an engineering and scientific feat to design and create an instrument sensitive enough to detect gravitational waves. And for that, these three individuals who helped lead the mission, they received the Nobel Prize in Physics. And yeah, so it's an incredible discovery, and it's turned into actually a wealth of astrophysics since then. So these are the mergers that LIGO has, LIGO and Virgo. Virgo is a observatory in Italy, and together, so those three observatories can now search for gravitational waves together in an even better way than just LIGO alone could. So they've seen now, well, more than here, but this is just a sample of the first 11 events that LIGO Virgo saw. So there are black holes in the upper, lost my cursor, but there are in the upper region, these are the black holes. So these are all the black holes we know about. So there are EM black holes. These are black holes identified with electromagnetic radiation. And then there are black holes identified with gravitational wave radiation. And so we've seen most of these LIGO gravitational wave events have involved slightly heavier on average masses than EM black holes. And then there was one neutron star merger event in actually it's called O2, the second observation campaign of LIGO. And so anyway, so I just want to highlight that these are black holes that involve 5 to, I guess, 80 solar masses. Okay, so these are considered stellar origin black holes. Okay, black holes that came from massive stars that evolved and went supernova and then formed either neutron stars that eventually formed black holes, or actually just right out of the bat just formed black holes. So, however, we'll be talking about supermassive ones. So there are kind of two kinds of groups of of black holes that we've seen. So these small black holes are sometimes called stellar mass black holes or stellar origin black holes. They exist in they can exist in X-ray binaries, which an animation is shown in the lower left-hand corner of a star orbiting a black hole, and those tend to range around 3 to 100 solar masses. And the ones that we've seen in light are usually galactic, so they exist in our galaxy. Those that we see with LIGO are extragalactic, and they can actually form these powerful jets. So an example of a jet is in the lower right-hand corner, but this is for a supermassive one. However, jets are seen in stellar mass black holes too. So anyway, black holes are great for understanding how stars evolve, the stellar mass distribution of systems. They also tell us how matter behaves in the strong field regime of gravity. Supermassive black holes, these are black holes that have maybe formed from really massive stars and then have accreted a whole lot of gas over cosmic time to get to the size they are. We don't quite know how they form and evolve, so that's why we want to use gravitational waves and EM to find how they evolve, and we're still doing that. But these things are 10 to the 5 to 10 to the 10 solar masses. And as I said, that there's at the centers of galaxies, they form jets. They can tell us how galaxies evolved. There's feedback, so black holes, jets, and outflows from black holes feed back into the galaxy, alter star formation, and do all sorts of crazy stuff. So, but really, I'm interested in understanding plasma physics in the strong field regime of gravity, because there's nowhere else in the universe that you can do this. And so more about supermassive black holes. Well, so yeah, so they're the only system of black holes that you expect to have lots of gas around. And that means that they're going to be emitting a lot of light. So there's a term active galactic nuclei. They're active because they're very bright and luminous and they're shooting around lots of gas. So we want to look for those systems because we want to find them in the electromagnetic regime and sector, and also the gravitational wave sector. And primarily, I'm focused on Lisa sources. So these are, there are a range of gravitational wave waves that you can look for. those that vary at, that have frequencies of hundreds of hertz to, those are LIGO sources, to millihertz systems, which are Lisa sources. And then there are these things called, this type of detection called pulsar timing arrays. And I'll go into that next. But anyway, so we're going to be looking for these things in the with light, and we are going to take advantage of these new generation of telescopes that are robotic. They constantly scan the sky, and they scan it every few days. So we have like a movie of the whole sky, and we can see how things are varying, and we can search for these new types of systems. So we haven't discovered a supermassive binary black hole in the in-spiral regime yet. So that would be a new discovery, and we're looking for them because we're interested in these systems and also future Lisa sources. So which I'll talk about soon. So LSST here I mentioned is the Large Synoptic Survey Telescope, and it's a big robotic telescope that's going to detect hundreds of thousands of AGN, and many of these we hope are going to be binary AGN. So we hope we'll get enough statistics to find these binary AGN, and however, we don't know what to expect. So we need to do accurate simulations to really know what to look for, so that we can pick these needles out of the haystack. So as I mentioned, there's one way of hearing gravitational waves called pulsar timing arrays. So there's this movie on the bottom that shows a neutron star that is emitting this light. It's called a pulsar, and this light, so neutron stars spin at a very even rate, okay? And this lighthouse effect of the pulsar then sweeps this light at us at a very constant rate, at a very predictable click. And these clicks can be recorded. We can observe a pulsar, and we can measure the time between these clicks, these pulses, and we can see if they vary over time. And this variation could be due to a gravitational wave transiting the space in between the pulsar and Earth. And if we have a network or an array of pulsars, then we can use this timing offset to notice the gravitational wave passing one pulsar and then the next. And then we can use that to triangulate maybe the source of the gravitational waves. However, we need a lot of pulsars to do this. And so right now, there are these radio telescopes that are searching for more and more pulsars so that we can keep on listening to them and see if we measure any time offsets. So pulsar timing arrays happen at the nanohertz regime. So this is a noise, this is a characteristic strain. So these black curves are the sensitivity curves of these instruments, and the color shapes are signals from different sources. So pulsar timing arrays are sensitive to 10 to the 9 to 10 to the 10 solar mass black holes, binary black holes. Whereas Lisa, it's sensitive to around 10 to the 5, 10 to the 6 solar mass black holes, and LIGO is around 10 to 100 solar mass black holes. So they explore different regimes of black holes and different, with their different regimes of gravitational waves. And however, we're likely to see counterparts to pulsar timing array sources, but we're not really expecting to see them merge because they evolve too slowly. They're too massive. And if we hear them, likely it's going to be too far away for it to in-spiral and merge in our lifetime. However, Lisa sources, if we hear them, they're likely to merge in our lifetime and in the lifetime of the experiment. And so we'd be able to see the whole range of evolution. So this is Lisa. So Lisa is a constellation. It's kind of like LIGO in space, essentially, but instead of just 2 arms, it's 3 arms. It forms an equilateral triangle, and it's going to be in orbit behind the orbit of Earth. Okay, So it's not going to be in orbit around Earth. It's not like your regular telescope, but it's going to be really big. It's going to span millions of kilometers to detect these really long wavelength gravitational waves. And in the lower left-hand corner here, we've got the strain plot that shows tracks in spirals. So this is the signal, gravitational wave signal of a 10 to the 7 solar mass binary black hole, and it in spirals, merges, chirps, and rings down. And so you can see these at different masses. And also, they're going to be sensitive to white dwarf binaries in our galaxy, and that's going to be a background source that is going to confuse us a little bit. But we're going to, since Lisa's so sensitive, we're going to see them. So we're for sure going to see gravitational waves. And there's some verification binaries that we know these binaries exist, and so we can look for them. We can pick out their signal and test the antenna with them. But we're expecting to see lots of order 100 of these sources well above the background. We can even see LIGO sources that start in the Lisa band and then go and then merge in the LIGO band. These may be harder to find though. So one thing that Lisa is great at is it can explore black holes evolve and binaries form and merge throughout cosmic time. So this is a plot of the signal to noise of waves from binaries as a function of redshift and mass. So if you're at around 10 to the 5, 10 to the 6 solar masses, we may be able to see them with, so the color contours are different signal to noise ratios. So 100 is the cyan color. So a signal to noise ratio of 100 is pretty good. You can get a lot of information out of that. And so you can see that out to redshift 20. That's crazy. Now, if we want to see like light from it too, we want to actually see it nearby. So we're hoping that some of these mergers happen nearby. But you can use the ensemble of binaries that you see to differentiate between models of formation and evolution between them. So these different tracks show you how black holes form differently and evolve differently. And if your population doesn't match with one evolutionary track, then it'll support maybe another model. So this is going to be a really exciting time for astrophysics, because it's hard to do this any other way. So what's the electromagnetic evidence for binary black holes? Well, we see them sometimes have these, so the nuclear regions of galaxies can sometimes have these double knotted features in X-rays. And so this is thought to be, these are two black holes accreting. And black holes often are, if they're accreting, they're often bright in X-rays. So this is a way, and those X-rays, even though there's lots of gas in the nucleus, those X-rays can penetrate all that dense gas, just like X-rays can penetrate your skin in the doctor's office. So you can also use radio waves. So in the upper right-hand corner and actually all the plots on the right use radio waves, and they can show radio wave antennae are really big, and you can make rays that are really large, just like we're using the Event Horizon telescope. And you can resolve really small angular features in the system. So these are actually, radio is the best way to really see the smallest angular features of systems out there. However, sometimes radio is obscured by nuclear gas. So anyway, there's evidence in the radio for double nuclei. However, all of these systems that we've seen so far don't get any smaller than around maybe 0.1 parsec. So that means that it's not really close enough to be really bright in gravitational waves yet. So we want to actually see things that are closer together, and that probably means we won't be able to spatially resolve them. So we have to look at their modulation, how their light changes over time. So people are making catalogs of these binary candidates for dual AGN. We're actually interested in binary AGN, which are even closer than duals. In any case, there's this whole campaign going on. there are people looking at the light curve, how the light varies, and they have identified modulated signals, and with this modulated model, and assuming it has to do with the orbit of the binary, then you can say, well, it's this particular system has a separation of 140 to 1400 m. So we use units of m. Things scale with the mass. M is the mass of the system. So that's a natural scale of this determines the dynamics of the system. So in any case, so this system would spiral in 10, in a million years. Not really what we're looking for, but still, this could be an interesting system to follow up on. However, and another group found one that was actually going to spiral in 7 years in its rest frame. And that's really exciting. It has a period of half a year. We were really, really excited about this. However, then this group followed up with more data and found that the longer baseline data did not match their fit. So this is highlighting the problem that you actually need to see more than 5 cycles of an oscillation in order to really convince yourself that it's not due to just statistical red noise fluctuations. Okay, so AGN actually vary in this red noise sort of way, and that red noise can look like a periodic signal at long wavelengths or low frequencies. And so you have to make sure you actually cover many cycles in order to really convince yourself. So there's no really convincing binary object yet. Duals, they're all out there, and we're pretty convinced they exist, but not something that's going to merge in our lifetime yet. So we're inspiring a field that is going to search for these things, and in particular, ESA, the European Space Agency, is thinking of launching Athena and Lisa together. Athena is the next generation X-ray telescope. They're thinking of launching them together so that they can use the X-ray telescope to look at these counterparts. And I just want to put this out here. The Astro 2020 Decadal Review is underway too, and this is a big theme of the Decadal Review, at least in my point of view. So what's the strategy that we're using to simulate these things? Well, we want to start from the black holes in the in-spiral regime and have them go really close to merger. We're using post-Newtonian techniques, so we don't really solve Einstein's equations in full numerical relativity, but we use post-Newtonian techniques so that we can really just focus on the gas dynamics. So, and then we know from numerical relativity simulations what the waveform looks like, right? So that's been solved for a long time, well, for at least about a decade. But the matter dynamics is kind of the frontier. So we start with something we assume that there's been this evolution, that black holes have come from galaxy mergers. Those black holes settled into a core, and they then eventually entered the in-spiral regime. How they got there is still somewhat of a mystery, but we think that it's been solved by non-spherically symmetric distributions of stars. And then we will copy or transfer our data to a numeric relativity calculation so that we can do the merger and see what the merger signal is. So the key challenge is really to resolve the dynamics from the black holes scale to the scale of the circumbinary disk. So here you're looking at top-down views of the gas. This is density of gas moving around the black holes, and these are the white dots around the black holes. Here we've kind of ignored the gas near the black holes, and here we're covering the gas near the black holes, but not the gas in the center, and I'll get more into that. So black hole accretion disk theory. So you've got a jet corona that emits X-rays, and you have the bulk of the disk that emits X-rays and UV light. You need MHD, ideal magnetohydrodynamics, GR, radiative transfer to carry the photons to a simulated camera in the distance, and you also need to understand how the temperature of electrons and protons vary. However, we're just focusing on the MHD, GR, and the ray tracing. So the magnetorotational instability allows gas to lose angular momentum and to transport it to a larger radii, and it's the mechanism that explains how systems accrete efficiently at the rates that we observe them. There's no other mechanism that we know of that is so efficient at accreting, getting gas to accrete. So we really think that in order to accurately model these systems, we need to evolve magnetohydrodynamics so that we can study the instability. Here you just see field lines threading an annulus of gas that is orbiting into the board on the left-hand side and out of the board on the right-hand side. So we're moving along this disk of material, and disks, if they follow a Keplerian rotational law, their orbital velocity increases as you go to smaller radius, but the specific angular momentum decreases as you go to smaller radius. And so two fluid elements connected by a coil, which is really a magnetic field line, it wants to move faster, so it stretches that field line. That tension in that field line then pulls on this one, giving more angular momentum to this one, so it moves outward. And this one is pulled backward, and it's given less. It's taken away angular momentum, so it wants to move inward. So then the tension in the field line increases, only exacerbating the problem. So this is a nonlinear, eventually reaches a nonlinear phase, and then inspires turbulence, which you can see in this figure. So this is a single black hole. This is an edge-on view of gas, of log of density of gas accreting onto a black hole. So this is a really thin disk, high-resolution thin disk simulation, one of the first that we did, and it shows you just how turbulent and chaotic these disks are. But you have to do all this crazy dynamics to accurately model how accretion happens. So the PostNewtonian scheme that we use is developed by Nico Yunus and collaborators, and it was really designed for numerical relativity simulations. And these numerical relativity simulations would start with this data as initial data, and then they would evolve Einstein's equations. However, we want to actually use it to evolve the space-time forever. And we can do this because the black holes that we're starting from are not really close together. We're in the post-Newtonian regime. So post-Newtonian just means we're perturbing, we're finding solutions to Einstein's equations of GR to some perturbative order, 2.5 post-Newtonian order. And what we do is we perturb in the quantity m1 over r or m2 over r. So m is the mass of one of the black holes and r is the distance to that black hole. And we also expand in v over c. So those are the expansion parameters, and we expand to those orders and then truncate it. And that's our approximation to the spacetime. This allows us to get like a closed form expression. It's just a function call in our program that says, give me the spacetime, and it returns the spacetime, and then we use it however we want. So it kind of eliminates all the difficulties of evolving Einstein's equations for us, and we can focus on the matter. But it also includes all the rich dynamics. It includes radiation reaction terms, so the black holes do still in spiral, and everything is handled self-consistently. But it's different approximations in different regimes. So near the black holes, they're post-Kerr or post-Schwarzschild. So it's a black hole with perturbations. The perturbations are from the other black hole, and that is the inner zone here shown in the lower left-hand corner, represented by IZ. So there are two inner zones for the two black holes, and then there's a buffer region that kind of interpolates between the inner zone and the near zone. And the near zone is the region that surrounds the black holes immediately, and then the near zone has a buffer region buffer zone that connects it to the far zone, and the far zone is the wave zone, which is the approximation is post-Minkowski. It's just flat space with waves on top of it. So we use this to for our spacetime, and you can see we've measured how well it is at preserving expectations of what a black hole spacetime should look like. So the Ritchie scalar, which is shown in these colored contour plots on the right, show the Ritchie scalar distributed over space at two different orders: first order on the top and second order on the bottom. And the left and right columns just showed different focus on different regions of the spacetime. And you can see that the Ritchie scalar, so in GR, the Ritchie scalar should be 0 everywhere. Here it's small. It's smaller for the second order, more accurate case, which is what we expected. So that's good. And it's only large in as you get really in the buffer zone as you get to the black holes. So this is, I mean, at the second order scheme only gets to be about 10 to the minus 3. And that means that there's some fake mass in the system, but it's distributed smoothly around. So it probably doesn't have much of a dynamical effect. And we've actually measured this in different ways, and we're pretty convinced that this is working pretty well. So what this allows us to do is simulate hundreds of orbits of black holes. So the numerical relativity calculations can't do that efficiently. And so, especially with matter. And so this allows us to let the disk settle into a steady state, so that we're pretty confident that this is a natural or realistic looking accretion system. And these cost usually like 1 million CPU hours on computers. So they're pretty expensive, but we can do them with the supercomputers we have today. And this one simulation that I showed you here, actually we discovered a novel periodic signal in the light. So what we did was we cooled the gas. That gas was cooled by radiation. We recorded the radiation that the gas emitted, and then we integrated it over the volume to get the light curve. That light curve has a signal, had a periodicity in it, and we took the Fourier transform of it, and we see here it happens at around 1.5 binary orbital frequencies. You would think, well, hey, you know, the periodicity of the light signal should be close to the period of the binary, right? Because that's what's mixing things up. But we found that actually it's 1.5, and it's because most of the light signal comes from gas that is tidally torqued. So gas wants to fall into the binary, but the binary has this quadrupole moment that's time varying, and this turns into a tidal torque. So it torques the gas. Some of it is expelled out into the circumbinary disk, and the rest is accreted to the black holes. So that stuff that's flung back out, that's torqued out, is crashes into the disk that's triggering the accretion. So here on the right-hand side is a movie in rotating with the lump. So the lump is an over-density region. So this is density of the gas. So this lump develops. It's the red to white feature, and it orbits orbits around the black holes at a rate a little bit less than the black holes. And so we're in the rotational frame of that lump, more or less. And so we see that these streams keep on shocking against that lump, and that shock heats the gas, and then that hot gas then radiates the light. And this is the brightest feature of the disk. And so what happens why it's 1.5 times the frequency of the binary orbit is because it's the beat frequency between one of the black holes passing by the lump. So, and it's 2 times because this happens twice, because this is an equal mass binary black hole. So this is a non-trivial manifestation of gas dynamics around a binary black hole that we wouldn't have discovered if we didn't do the simulation. And so in order to actually carry the gas to the black holes, so there we just ignored the gas that fell into a spherical region around the black holes, but in order for computational efficiency. Now we want to see how the gas actually falls onto the black holes themselves. So we need to create a grid that resolves the gas dynamics near the black holes. And we do this using this warped grid scheme. So we warp or focus the cells on which the equations are solved. And we focus the cells around the black holes so that we can really pick out the small scale features that happen near the black holes. And we've done this. So the first paper was 3 orbits that we could do, and we could afford, because it is an expensive calculation. And the top movie here is a 3D rendering of the density, and the bottom one is the same rendering but further out, and the white lines are magnetic field lines. And this was the first realization of mini disks forming around black holes, fed by with MHD, with NGR, and we found that the mini disks, even though we started with them, they quickly depleted, but then they were replenished by the circumbinary gas, and this replenishment happened periodically as the black hole passed by the lump. So as it left near the lump, it depleted, right? The black hole, the gas accreted onto the black hole, and then after it was depleted, it passed by the lump again, and then fed from the lump and was repleted. And so this created this scene here where we plot the mass fraction in each mini disk. We see that as one is increasing in mass, the other is decreasing, and vice versa, because they're out of phase with the lump. And so this modulation wasn't expected, and so it manifests from the fact that there's this lump of material that orbits the black holes, and that lump of material modulates the mass accretion rate and likely the light curve. So in order to calculate the light curve, we do this general relativistic ray tracing, where we transport light, a full spectrum of light, through the disk, from the photosphere, through the corona. We have a corona model, which is a non-thermal model where we assume that the corona is at a fixed temperature. All the details are given in this Descali paper. I won't have time to go through all this, but anyway, we want to calculate the whole spectrum of light coming through this. And because we have a simulation, we can look at how it varies in time. And so here, this is just a demonstration that we can show you, we can calculate the ultraviolet light and the X-ray light. And we see here the X-rays come predominantly from the mini disks. That's where the hottest temperatures are. Notice also there's this, what may look like a third black hole, but this is not a black hole, this is just a cutout. So because of how we've designed the coordinates, we can't actually cover this region, okay? But there's very little gas right there. However, we want to change that in the future, and we have. But for this calculation, which was a first of its kind, we were still limited by this fact. So don't get confused by this black spot. These are the black holes over here and over here, the ones that move. So this is the spectrum. So this is the first spectrum calculated from magnetized accretion onto binary black holes. And we broke it up into different components: the circumbinary disk component, the mini disks that are orbiting the black holes individually, and the accretion streams that connect the circumbinary disk to the mini disks. And then this is just the total. We see that the mini disk spectrum actually varies the most, right? Because it's the most dynamic one. And we're hoping that this modulation, even though we didn't have much time because we only had 3 orbits of evolution, that this modulation will give us a light curve that we can use to identify these systems. Also, we can measure the spectrum of AGN and see if it matches this spectrum. So there are key aspects that we can look for are, well, binaries are expected to be brighter in X-rays than a typical AGN, and it's also supposed to have a slightly broader thermal peak. So a binary, a single AGN would drop like so, maybe peak at a higher temperature, but it won't be as broad as this because of the mini disks. So the presence of the mini disks and the enhanced shock that happens between mini disks, the accretion streams falling onto the mini disks, that will broaden this thermal peak and may actually make this little notch here apparent. So that would be also a signature to look out for. So here you can see a time average of that, and the width of the curve is proportional to the standard deviation of the variability of that curve. So you can see the mini disk accretion is really the most variable, and so we hope to look for that variability. Also, angle dependence. So since we didn't have a whole lot of time to integrate over, we were using how, if we saw this at a high inclination, if it was edge on, how much it would vary. We see that there is an angle dependence. So those that are more edge on, we see greater variability, and that's represented in the right-hand plot. So theta cam is the angle from the z-axis that the camera is at. So 90 degrees is when you see the binaries in edge on view, and theta 0 is face on. And then phi cam is the angle around the orbit of that the camera is at. So we're like moving around in the same way as the orbit. And you can see if the black holes are lined up, then one is lensing the other, and that boosts the signal from the background black hole and then increases the light there. So that orbital modulation will be present, but probably not as strong as the accretion rate modulation. So we produced with NASA a movie of our simulation work, and you can see the whole movie here at this link below. I don't have time to show you the whole thing, but I encourage you to pause the movie, copy this link into your browser, and look at the whole thing, because we're pretty proud of it. But we now have longer simulations. So we did 12 orbits using the same grid. We just ran the simulation longer, and we saw really strong evidence of this depletion, repletion process of the mini disks. We found that it kept on going. Just to remind you, the grid looks like this. And we now have enough data to get a really good light curve out of it, and that's being processed right now. And we see this is a plot of the mini disk mass for each mini disk as a function of the orbits. And then on the right is a Fourier transform of it. And you can see how different components modulate at different frequencies, and how it relates to the phase difference delta phi between the binary orbit and the lump orbit. So each component has that component with the phase of the orbit, but not all the components. And there's some that have that double beat frequency power, but not everything. So we're still so in the next plot we see this is plotting the mini disk mass of 1 to the total, and you can see how it really increases to a large fraction of the total mini disk mass, and then it quickly accretes, and then it increases again. So this is a pretty strong periodic signal, and we expect that to be really dictate the light that we see from them. Now, we've eliminated the weird circle at the center of our grid, and what we did was we covered it. We have two patches of coordinates. So we have that a spherical-like grid around the circumbinary disk, and then we have a Cartesian grid around the black holes. So that allows us to get rid of that circle and cover the whole domain. So, and it's more efficient, so we've been able to do 30 orbits. So we even have more data, and we can see how, because there's no gap in the middle there, these accretion streams can flow right through from one mini-disk to the other. And we're thinking that this mini-disk interaction will then also create an interesting light signal. Unfortunately, I don't have those results ready yet. These are relatively new simulations, and we're still processing them with our ray tracing code. But this is the first of a kind where there's no gaps in our volume. We're covering the whole thing, and we're doing it completely well. And also, I want to point out, these aren't just thin disks. They have thickness, and this thickness varies. And so there can be accretion coming kind of above the black holes onto the black holes, because the streams are kind of relatively thick compared to the black holes. We're now working, this work is in progress, working on analyzing that. However, it compares well to our previous work with the warped coordinates. And however, we didn't start with mini disks in this patchwork run. In this latest run, we just let the circumbinary disk fill in the mini disks, and we still see similar periodic structure, but slightly we have. So this is the old power spectrum, and you can see that the new power spectrum, there are new features at the low frequency that were in there, and the frequency at 1.5 omega bin seems to be double peaked now. And so we're trying to figure out where these new features are coming from. The more detailed power spectrum is due to the fact that we have more orbits of data, more time of data. Our data set is longer in time. So we're still trying to figure out if the sloshing between the mini disks, sloshing of gas between the mini disks is the cause of this, or some other feature. So I just want to quickly, I think I've exhausted more than enough time. Supermassive binary black holes are really exciting. They're important gravitational wave sources for Lisa, and we're hoping to find them with light very soon, and so that we can study them both in both sectors, light and gravitational waves. And I'll welcome any questions you have. Thank you very much.
Hello, Scott. Thank you very much for this nice webinar. It's impressive, the amount of work and the simulations and the pictures and the videos are amazing. You have been doing a very great job. We have a question from, well, a couple of questions. One is from our YouTube channel. I copied it on here on the chat, but I will read it. And it's related to the introduction of your talk. So they say, if we detect an offset in pulsar timing, how would we know if it was caused by gravity wave versus pulsar physics?
That's a very good question. And unfortunately, I'm probably not the best person to ask, but I know that we know a great deal about pulsars. We're learning more and more about them, and we can study their pulse history. I mean, they pulse very rapidly. I mean, some pulse with periods of milliseconds, and most longer. But so we can, when we observe them, we can get a bank of 1,000 pulses, and we can study their history and see if these changes in the timing are due to glitches in the neutron star, and that's been observed before. So, but those glitches are also associated with changes in the pulse structure too. So I think with enough statistics and understanding of the pulse shape of each pulsar, we can then differentiate between a glitch and a transiting gravitational wave. that's my relatively novice answer to that question. But if you're really interested, I can put you in touch with people that are experts in pulsars. But yeah, that's a really good question.
Okay, thank you, Scott, and also for our viewers. We know that there's a 20 seconds delay, so if somebody wants to make a follow-up questions or something, we have to wait a little bit, and then it will be read to Scott. I also received another question. Well, I'm gonna try to do my best to read the question, but in the sense that, like I say, what would you say to young scientists or like researchers, particularly in South America, about your field, in the sense that in order to do those simulations, you need supercomputers and high performance computing facilities, but also the codes. Okay, the codes are like very complicated nowadays and advanced. So how would you say, like, for young scientists, how can they like start in that field? How can they move to that field, or what would be your advice? I think that's what that
yeah, no, I do acknowledge that it's challenging. There, you have to learn, general relativity, fluid dynamics, and then you need to know how to program, learn how to use supercomputers. I don't get overwhelmed. Do one thing at a time. Start using computers as early as you can. That expertise builds upon itself over time, and you just become more and more confident, and you can. It is something that I've found using computers is that time and experience does help. I mean, you get better and better, and that experience feeds off itself. Don't be afraid to tinker with programs and play around with programs, write your own, learn about operating systems, knowing how a computer works. I think probably that right now I see as a big challenge in the younger students, that our computers are pretty easy to use. So I grew up in an era where computers were hard to use. So you had to often get in there and figure out how to fix it, reprogram it yourself. And so that experience then was like, okay, when I had to then go write my own program, I kind of knew how to do it all anyway. So, but right now, you click on an app, it works. You can send a picture to someone on your phone really easily. But all that before, we had to like upload, pictures to an FTP server. We had to figure out what the command line of that was. My sensor is turned off. Hope you can see me. And so, but yeah, so I like, if you want to get into scientific computing, I would encourage you to get a Linux distribution, and that'll allow you to more easily program, in my opinion. You can use Python. Python is a good entry language to start programming in. But really, I think in order to do scientific computing, you need either C or C++. I would not encourage you to learn Fortran, but some people use Fortran. And I use Fortran in grad school, so there's nothing wrong with it. It's just that I think more people speak the language of C and C++ these days. But yeah, just start doing it. Get in contact with people that whose research you find interesting, and get their advice, and maybe work with them. You can these allocations people can use. We have teams. We have students, grad students in Argentina that are working with us and are using our allocations on these big supercomputers. So it's possible. So you don't have to be in the States to use them. And you can team up with people that have these resources and use them. And in some codes, there are communities that you can use to learn from. So the Einstein Toolkit is a numerical relativity code, and it has a pretty extensive and welcoming and nurturing community that can help you with problems. has lots of examples and things. So I would encourage you, if you're interested in that kind of field, to go that route.
Okay, thank you, Scott. So again, if there's a follow-up question from that person, you can do it, and then I'll tell it to Scott. So do we have questions from our law physics coordinators?
Yeah, I have a small question. I mean, very impressive, all the work that you have done, Scott. I mean, with all your collaborators, of course. The one question, because there were like 2 or 3 years ago when they started all the signature from gravitational waves, in which there were some coincidence signals that Fermi, Ice Cube, so on. Is it because you talk about mostly radiative process transfer, but could you also extract signals, for instance, neutrino fluxes from the disk, the accretion disk, and so on? In principle, I mean, like to add an extra observable to the signal.
Neutrinos.
Also, I mean, just to finish that, and shouldn't be difficult to implement in your code, or is mostly straightforward?
Yeah, our code doesn't necessarily, like, our code isn't a function of the mass of the black holes per se. So we can use our simulations to model stellar mass black holes or LIGO black holes. Mm-hmm. The radiation does it is parameterized by the mass, but we could readjust the parameters and redo the ray tracing to get a new light curve. So that's with the light. So in order to look for Fermi saw what a possible coincidence. Fermi is a gamma ray telescope, NASA gamma ray telescope, and it saw a blip right coincident with the first LIGO event. However, it was the line between the LIGO event and Fermi it just skimmed the atmosphere of the Earth. Okay. And so that they think that maybe the reason why they think it may not be real is because Integral, which is another gamma ray telescope in orbit, would have seen it and did not. And so they think that Fermi just picked up some gamma rays coming from the atmosphere. But but from those Fermi results, people came up with lots of different theories that could predict it. Like, for instance, actually kind of my favorite one was one where there are these dead disks around the black holes. So the gas is just orbiting each black hole, but not accreting onto it. So they're relics from a prior time. And then as they get closer, the gas kind of gets heated up more and becomes more magnetized, and then allows it to accrete rapidly as the black holes merge. Not really sure if the matter dynamics is really consistent with what we know about matter dynamics and about dead disks and why they would be there and why it would be stable for so long. I'm not sure anyone has done a really consistent calculation of that, but I thought that was neat. I mean, it's maybe theoretically possible, but it would have to be, these objects are also really pretty far away. So the luminosity also scales with the amount of mass you have there, right? Mass of the gas. The mass of the gas around these systems is going to be a fraction of the mass of the black holes, right? And so since these things are so far away and they're not very massive, they're not going to be very bright signals, even if there was, a bit of gas there. Neutron stars are, LIGO saw the GW 170817 event. It was pretty close, we could see them gravitationally and also electromagnetically because it formed a kilonova signal and a gamma ray burst. It wasn't even a pretty powerful gamma ray burst, because it wasn't really pointed at us, but its proximity helped. And I think the neutrinos, we did not see neutrinos from that, even though it was, there was a lot of nuclear material, there was a lot of nuclear decay, and I think, I'm not really sure how we can improve our chances for seeing the neutrinos from these events. Now for binary AGN, so there, just past year or so, they saw a blazar. So blazar is essentially an active galactic nucleus, a supermassive black hole that's accreting and has a jet that's pointed right at us. And they saw a burst in blazar activity coincident with a neutrino burst. So IceCube saw energetic neutrino come from the same region as the blazar at the same time as the blazar ramp up. And so they think that that was a multi-messenger observation of AGN activity. So one could imagine if there were two blazars inspiraling and merging, you could see the gravitational waves, the neutrinos, and the electromagnetic waves all at once. So it would be a three-messenger event. So that, I think that's why supermassive binary black holes is so exciting, is because there's going to be gas, there's going to be gravitational waves, and there can be even neutrinos from the blazar jet processing. So you have to be lucky, right? But yeah, I don't know. The neutron star mergers and neutrinos, I think maybe there's a chance there, but I need to look into that. But, thanks.
Okay,
thank you.
And do we have any other question from the coordinators? We
Yes,
might have a
yes,
couple.
one from me.
Okay.
So I do particle physics, right? So I'm gonna ask some very naive questions. So following Roberto's question, I was wondering if you could get a signal, for instance, dark matter on the accretion disk, right? Because in principle you should have it right there, right? So if it could annihilate in some very specific channels, so maybe well, wondering if you could actually say, oh yeah, we're having some extra contribution to this X-rays or whatever we're getting. So would you be able to tell that?
Yeah, yeah. People are looking into that, the theoretical predictions of dark matter collisions, annihilations, because black holes are, they're good at attractors of particles, so they can actually increase the efficiency of collisions of dark matter, and so because if you have a cloud of particles around a black hole, the density increases as you get closer to the black hole, and the scattering cross section of dark matter interactions scale at as rho squared, and so that then naturally means that these collisions are going to happen more and more closer to the black hole. So yeah, actually, my colleague across the hall from me, Jeremy Schnittman, has calculated this, and there have been estimates about the flux levels of Sagittarius A star at the center of our galaxy, whether or not we can see dark matter signals from there. I think there was actually a paper that supposed that what they saw was actually from Sag A star. I think all these signals are observed in the gamma rays because of the rest frame, the mass of the supposed mass of the dark matter candidates. I think it's in the GeV scale, if I'm not wrong, MEV or G. No, it's in the GeV scale. So that would make it a gamma ray. So that's why I think people are focusing on the gamma ray emission. And there, in order to really be convincing and that it's not some sort of like jet consequence, you would probably need like really high spatial resolution. And gamma ray telescopes don't usually give you that. In terms of binaries, yes, certainly if that could even accelerate further the interaction rates of the dark matter particles. I don't know if anyone's looking at the dark matter project in the regime of a binary. That could be interesting. It'd be harder because you have a dynamic space-time, but we do have codes to do that sort of thing. So to follow geodesics in a binary space-time. So yeah, that would be really kind of interesting. But yeah, I think there are theorists doing this. There are people looking at data too. So this is certainly on people's radar.
Super. And I have another naive question. This is even more naive. So you're going towards the merging of two black holes, right? And so in principle, nothing can cross an event horizon, right? So what is going on with the event horizon when two black holes merge? I mean, we in principle see it, right? So I'm wondering what's going on with the event horizon that allows the two black holes to actually merge.
So yeah, so we see everything outside the two event horizons, but as two black holes get closer, actually the way this happens is really interesting. You can get these caustics. So the event horizons is a three surface, right? It's like topologically a sphere, but it can, as they get closer, they can touch at a point. In order to look at the event horizon, though, you need the full 4D space-time of data, because the event horizon is defined as the last surface of scattering of photons that reached infinity, right? Future infinity. That means you need all those photons at future infinity to integrate backward in time to see where that last scattering surface is, right? So it's, in practice, that's not what's done. What's done is you calculate something, you have a spatial slice of your space-time, and you look for apparent horizons, and those apparent horizons are guaranteed to lie within the event horizon of the black hole. And so you look at how these apparent horizons form and merge. Those apparent horizons
is it apparent horizon?
Yeah, an apparent horizon is where the light rays kind of bifurcate, right? It's a surface at which the light rays bifurcate. So you can do this in a way that is only determined by conditions on a spatial slice of the space-time. So you can phrase this as like a Cauchy problem, as a initial value problem. And so you can look at these. It's easier to look at the apparent horizons forming and merge. Usually what happens is the apparent horizons get close, and then suddenly the outermost apparent horizon actually encompasses both of them. So the universe is always kind of being shielded by all the weird stuff inside. So there's usually this discontinuous jump because all these things are done with computers. Everything's discrete too, right? So there's always that discontinuous jump between the two apparent horizons and one apparent horizon. If you want to look at the continuousness of it, you have to look at the event horizons, and then you have to do the ray tracing from distant future observer backwards and track how those light rays travel and escape and arise from the black holes. And that determines the event horizons. And there you can have them form these really cuspy shapes that merge and create this long filament structure. And then that touching point grows, and then they create like this dumbbell shape, and then they form more or less a one black hole. So there's nothing, I guess, nothing that breaks that condition that nothing can escape an event horizon. One could say, well, where does the gravitational waves come from, right? Nothing can escape an event horizon. How do gravitational waves arise? Well, that's because there are these 2 point masses that are churning up space-time. It has nothing to do with event horizons, really. It's just any sort of 2 point masses on an orbit forms this quadrupole potential, and this time-dependent quadrupole potential then emits gravitational waves. Anything makes gravitational waves that moves in a certain way.
Okay.
I don't know if I answered your question, but
yeah. I understood it was even much more complicated than I thought.
It was not naive whatsoever. Yeah.
Thank you very much.
You're welcome. Thanks.
Okay, thank you, Scott, very much. And if people want to ask him questions, they can email him or follow him on Twitter. And let us see us in 2 weeks with another webinar. And let's thank again, Scott.
Great. Well, thank you, everyone. And yeah, this was great. Thank you very much.
Okay, bye-bye.